Though many take it for granted today, water has not always been a constant in the lives of human beings. With this being said, in the words of Vitruvius, water is an absolute necessity for life, for pleasure, and for daily use. And so it follows that water must be present, in one form or another, wherever humans are. In the early years of human life, this presence would mean one of two options. Option number one would be to live close, near, or along a water source. And option number two would be to find a way to contain water in a way that makes it easily portable. Now, both of these options are going to have their obvious limitations. Option number one is going to limit your location, so you can only live within a certain distance from a body of water. Option number two has another obvious implication, that is, even after you find a way to contain water, wherever it might be, you're going to need to find a way to also transport that water to wherever you wish to go, through the use of, human labor or animal labor, or perhaps even a combination of both. But as you know, water isn't exactly light, so again, this limits the distance that you can travel from the place where you get the water. Now, clearly this is an antiquated dilemma, as we can now simply go to a faucet and choose to be bestowed instantaneously with a seemingly infinite supply of cold, clean, and potable water, and a not-so-infinite supply of hot, clean, and potable water. But how did we get to this point? It likely seems obvious that we did not arrive at modern plumbing without prior innovation. This is absolutely true, and along the way there are many steps taken through construction and engineering to work toward a better solution for water for mankind. And today I'm going to be talking to you about what I think is perhaps one of the biggest bridges between ancient water technologies and modern water technologies, and that would be the Roman Aqueduct. Defined by National Geographic, the Roman Aqueduct was a channel that was used to transport fresh water into highly populated areas. Now, the concept itself is rather simple, and the science and engineering behind it can pretty much just be summed up into the understanding of how gravity works. And I'm going to insert a little demonstration here now to just sort of give you a basic idea of how an aqueduct would work on a small scale. Okay, so here's a little bit of a demonstration of a mock aqueduct. So I'm going to turn this faucet on a little bit, and we're going to pretend that this is just a running water source like a spring or a stream. And what I have here is just a straw that I've cut the end off to be able to funnel down the water. So let's say we have this little Lego man down here, and this is a hot spring, and he needs to get water there from over here. Okay, so this should work. I'm going to put the end of the straw here, and it should funnel the water out over there. Okay, so this is actually rather simple, and I'll show you from the side of it. The angle that I'm using, it's about this kind of steeper angle. Okay, so I really doubt that anyone was surprised that worked. After all, we all know that straws are great tools for transporting water, even if it may be down instead of up. So I'm going to show you now, though, something that made the aqueduct construction a lot more difficult. And this is something that shows just how meticulous the Romans actually got. Okay, so here's a little bit of a dilemma. My Lego man has moved, and he's now deeper inside the city, emphasized by the fact that he is in this dinner bowl here. But here's the problem. Let's turn our fresh water source back on and use the aqueduct again. Now, running it to the same place you're doing, we're going to see, obviously, it's not long enough to get to where the Lego man is over here in the bowl. Now, this means a couple things. Obviously, the aqueduct is going to have to get longer, so we're going to have to spend more time constructing it. And secondly, we're going to have to lower the grade, thus raising up the aqueduct. So with a little bit more of very complex engineering, I have constructed a longer aqueduct. And let's go ahead and see if this works. Now keep in mind, the grade that we're going to have to use is not nearly as steep as it was last time. So we're getting the water over here, follow it over here, and we'll see. So there goes the water. Okay, so the thing that I really wanted to emphasize here was that the farther you go away from the original water source, the engineering of the aqueduct gets a lot more complex. This is because the water source is always in a fixed position where it cannot be moved, and thus relying on gravity, the aqueduct, the farther you go out, you not only have to build more, but you have to be more precise because the grade of the aqueduct has to be considerably less in order for it to properly transport the water to the destination. Let's move on to the building process. As we just talked about, the grade that an aqueduct was constructed at is a very important factor to its efficacy. As such, a large amount of time in the actual building process of aqueducts was spent surveying land. Now, this wasn't just done by eye. The Romans did have some tools that they used in order to try to get the grade of land, and I'm now going to talk about a few of these tools. There are a few different tools that people think that the Romans might have used, but the ones that I'm going to talk about today are two that Vitruvius talked about, and then another one that is in other historical accounts. So the first tool that I want to talk about is the Groma, which I'll throw a picture of on screen right here. So this is basically just a pole with a metal bearing on top of it, and on the top of it is a cross. And the cross has plumb lines, which are these weighted wires, or rather a wire with a weight at the bottom that comes off of the end of each arm. And the bearing on the top of the pole allows for the top to pivot, which lets the user survey the grade when the tool is in the ground. Now, this tool relies on your eyesight, so you need to be able to see on the side where the plumb lines are exactly in order to understand the grade of the land. And because of that, it's a difficult tool to use in wind. So the next tool that I want to talk about is the first tool that Vitruvius talked about the Romans having used, and that is the Dioptra. Now, this tool, which I will try to explain to you to the best of my ability, is a little bit more complex, but it was used for measuring both horizontal and vertical axis. And basically, I'll throw another picture up right here, but basically what it is sort of like a plate that can move on both axes, so, front and back and side to side. And then it has an eyepiece and sort of rulings on the top of it. And if you looked along it, you could sort of see and get a feel for an angle. And something that's really important to note with the Dioptra is that Vitruvius actually noted that there were some drawbacks to this tool in comparison with the next tool we'll talk about. And I want to say that from my own personal observation, a lot of these drawbacks stem from it being difficult to use. In other words, this relative complexity of the tool meant that there weren't that many people who were building the aqueducts that could fully understand just exactly how to use a dioptra. But if you could, it is possible that you could get a more accurate measurement than you could, say, with a Groma. Okay, so the last tool that I want to go into detail about today is called the Corbetts. Now, this is a larger wooden tool, and it's also known as a land walker in some accounts. So the thing is about 6 meters long, so it's a lot larger than these other tools. And it operates somewhat similarly to a Groma because it has these same plumb lines on the four corners, or rather 2 on either end of the instrument. And these would be used against notches that would be cut into the supporting beams that hold the top up, and that way you could measure the grade of something, but over a longer stretch of land. And it's worth noting that Vitruvius preferred the Corbetts as a measuring tool to the Dioptra. Now, exactly why this is, I'm not certain, but I'm going to go ahead and assume that it's because, 1, it was easier to use, and 2, the fact that it was superior to the other tools that the Romans had, such as the Groma, because when the Groma struggled with things like wind interference, the Corbetts actually has a secondary form of measurement that can be used either as a second resort when there's wind outside, or when there isn't, to supplement the measurements made with the main mechanism. So as I talked about, there's plumb lines on the 4 corners, but there's also a hollowed out part in the top beam that allows for water to be placed inside, and then you can survey the water and look in there and see if it's level or not. So the Corbetts is kind of unique in the sense that it actually uses 2 different methods for leveling. So in addition to having two forms of measurement, the Corbetts also had another advantage, which is that it was more rugged from it being larger and being built out of wood. So it wasn't quite as temperamental and could be used in many places. And because of this reason, it's commonly believed that the Corbetts was the tool most used by the common or rather more grunt type worker building these aqueducts, whereas some of the more refined tools, perhaps like the Dioptra, would only be used by higher ups. Understanding these tools can give us a little bit of insight into the way that the Romans actually surveyed the land to build an aqueduct. Of course, this surveying, well, it was, in my opinion, a bulk of the mental struggle of engineering around the aqueducts. The struggle was not over even once this slope, rather, was figured out, as everything still had to be physically constructed. So I'm going to go on to talk a little bit about that now. Something that is really important to note when we talk about the construction of the aqueducts is that what most people see as an aqueduct is actually a short section of it. Only about 30 out of the 260 miles relatively that the Romans built were actually above ground. Everything else was below ground in channels. Because most of the aqueducts were underground, this actually created sort of an additional challenge when physically constructing the aqueducts. And this was that if you start digging a channel on one side, you can really only go in one direction. So to expedite the process, what the Romans did a lot of the time was actually had their workers dig down channels along the path that they were building the aqueduct. So every 20 yards or so, they would dig down a new, essentially tunnel straight into the ground, the level where the aqueduct channel was supposed to be, and then work toward each other. This allowed for the process to go by a lot quicker than it would if you just had a group of people digging in one straight line underground. So when it comes to building materials, the Romans utilized a few things in the construction of aqueducts. The first of which I will mention are bricks and stone. Now, these are the most prominently used building materials on the Roman aqueducts, as it makes up pretty much all of them, the internal ones and the external ones. I haven't found any sources about this, although I looked, but it appears to me from the pictures that we still have that the exterior aqueducts utilize stone that is cut in a more aesthetically pleasing way than the interior of the aqueducts, which would make sense, as more attention to detail would make sense on a part where you could see, and also a part that is a substantially smaller portion of the total structure. But regardless of what the brick or stone looked like, it was held together by the same mortar. Now, this would have been this brick and mortar setup, the same setup that was used to construct many other Roman structures. But there is one building material that makes aqueducts quite unique, and that is waterproof concrete, which is a mixture that the Romans came up with that they pretty much coated the entirety of the aqueduct, interior and exterior, in. So if you ask me, the waterproof concrete is the coolest material that was used in the construction of the aqueducts, because unlike other concretes of the time, it had properties that would allow for it to withhold the erosive properties that a stream of water had. So this allowed for a few benefits. One, it allowed for a smoother path for the water in the aqueduct to travel along, and it also allowed for wear to happen a little bit more evenly, whereas if the water were running up right along more jagged stones, it could quickly erode a hole in the system and cause for water to leak, thus affecting the efficacy of the aqueduct. With the end of the discussion about building materials, I'm also at the end of this presentation. While I know that there's still more that could be talked about, I just wanted to give sort of a brief overview to help you understand the planning and construction process behind the aqueducts. What I think the big takeaway from my research and my project is that the Romans were super meticulous with their planning when it came to aqueducts. Now, this is particularly impressive because the tools that they used were not the most accurate, but they were still able to maintain these slight grades over miles and miles that the aqueducts needed to travel. And I think that makes this particular structures super impressive.